You're watching EduSpot. Learn smarter, understand faster. Let's begin.
Hello everyone, and welcome to this topic on neural networks. Today, we're going to explore one of the most powerful technologies behind modern artificial intelligence. Neural networks allow computers to recognize faces, understand speech, translate languages, recommend videos, and even drive cars. By the end of this topic, you'll understand how neural networks work, why they are so powerful, and how they learn from data just like the human brain learns from experience. Imagine teaching a child to recognize a cat. Instead of giving hundreds of rules, you simply show many pictures of cats. Eventually, the child learns to recognize cats on their own. A neural network works in a very similar way. Instead of following fixed instructions, it learns from examples. The more data it sees, the better it becomes at identifying patterns and making accurate predictions. This ability to learn from experience makes neural networks one of the most important technologies in artificial intelligence today. Traditional computer programs work by following rules written by programmers. If the rules are incomplete, the program fails. Neural networks work differently. Instead of depending on fixed rules, they learn directly from data. This allows them to solve problems that are too difficult to program manually, such as recognizing faces, understanding human speech, detecting diseases from medical images, or recommending videos on YouTube. Their ability to adapt and improve makes them much more flexible than traditional programming. The idea behind neural networks comes from the human brain. Our brains contain billions of neurons that communicate through connections called synapses. Similarly, an artificial neural network contains artificial neurons connected through numerical values known as weights. Just as our brains become better through learning and experience, neural networks improve by adjusting these weights during training. Although artificial neurons are much simpler than biological neurons, together they can perform incredibly intelligent tasks. The artificial neuron is the basic building block of every neural network. It receives information from multiple inputs, processes that information by assigning different weights, adds a bias value, and then passes the result through an activation function. Finally, it produces an output that is sent to the next neuron. Millions of these simple artificial neurons working together allow AI systems to recognize images, understand speech, and make intelligent decisions. Now let's look inside an artificial neuron. Every neuron has 5 main components. First are the inputs, which carry information into the neuron. Each input has a weight that tells the neuron how important that input is. The neuron also has a bias, which helps shift the final result and improves learning. Next comes the activation function, which decides whether the neuron should pass information forward or not. Finally, the neuron produces an output. These 5 simple components work together to help neural networks learn from data and make accurate predictions. Weights are one of the most important parts of a neural network. You can think of them as important scores. For example, if the AI is trying to recognize a dog, the ears and eyes might receive higher weights because they are important features. The background, however, may receive a much smaller weight because it doesn't help identify the dog. During training, the network continuously adjusts these weights until it learns which features are most useful for making correct predictions. Bias is another important value inside every neuron. While weights determine the importance of each input, bias gives the neuron extra flexibility. Think of it as an adjustment knob that shifts the neuron's decision. Without bias, the network would struggle to learn many useful patterns. During training, both the weights and the bias are updated together to reduce prediction errors and improve the model's accuracy. After calculating the weighted inputs and adding the bias, the neuron passes the result through an activation function. This function decides whether the neuron should produce an output. Without activation functions, a neural network would only be able to solve simple linear problems. Activation functions allow the network to recognize faces, understand speech, detect diseases, and solve many other complex tasks. Different activation functions are used for different types of problems, but ReLU is one of the most common in modern deep learning. Let's see how information travels through a neural network. Imagine we provide an image of a cat. The input layer receives the image as numerical values. These values move through multiple hidden layers, where each layer learns different features such as edges, shapes, eyes, ears, and whiskers. Finally, the output layer combines all this information and predicts the correct answer, cat. This entire process of moving information from the input layer to the output layer is called forward propagation, and it is the first step in every prediction made by a neural network. The next step is to check whether the prediction is correct. This is the job of the loss function. Imagine the network sees an image of a cat but predicts dog. Since the prediction is wrong, the loss will be high. If the network correctly predicts cat, the loss will be very low. You can think of the loss function as a teacher checking a student's answer sheet. It tells the network how many mistakes it has made and how much it needs to improve. During training, the network always tries to reduce this loss as much as possible. While the loss function measures the error for one prediction, the cost function measures the average error across the entire training dataset. Suppose the model predicts thousands of images. Some predictions are correct, while others are wrong. Instead of looking at one prediction, we calculate the average error. This average is called the cost function. During training, the AI tries to reduce this cost after every learning cycle. A lower cost means the model is improving and making more accurate predictions. Now that we know how to measure error, the next question is, how does the network reduce it? The answer is gradient descent. Imagine standing on top of a mountain in thick fog. Your goal is to reach the lowest point. The safest way is to take small steps downhill. Gradient descent works in exactly the same way. After every prediction, it checks which direction reduces the error the most. Then it updates the weights little by little. After thousands of small steps, the model reaches a point where the error is as low as possible. Gradient descent takes steps to reduce error, but how big should those steps be? This is controlled by the learning rate. If the learning rate is too small, the network learns very slowly and training takes a long time. If it is too large, the network may overshoot the best solution and fail to learn properly. Therefore, choosing the right learning rate is extremely important. A balanced learning rate allows the model to learn efficiently while remaining stable. Backpropagation is one of the most important algorithms in deep learning. After the network makes a prediction, it calculates the error using the loss function. Instead of stopping there, the error is sent backward through the network. During this backward pass, every connection updates its weights based on how much it contributed to the mistake. These updates help the network make better predictions next time. This process of making a prediction, measuring the error, sending the error backward, and updating the weights happens thousands or even millions of times during training. This continuous cycle is how neural networks learn from experience and become more intelligent over time. Now let's combine everything we have learned into one complete training cycle. First, the neural network receives training data. It performs a forward pass and generates a prediction. The prediction is compared with the correct answer, and the loss function calculates the error. Then backpropagation sends the error backward and updates the weights using gradient descent. This entire process repeats thousands or even millions of times until the model becomes highly accurate. Every successful AI model, from image recognition systems to ChatGPT, learns through this continuous cycle. An epoch means one complete pass through the entire training dataset. Imagine your dataset contains 1,000 images. When the neural network has processed all 1,000 images once, it has completed one epoch. However, learning usually requires many epochs because the model improves gradually with each pass. During every epoch, the weights become more accurate, allowing the network to make better predictions. Choosing the right number of epochs is important because too many can lead to overfitting. Instead of processing the entire dataset at once, neural networks usually divide it into smaller groups called batches. For example, if a dataset contains 1,000 images and the batch size is 100, the model processes 10 batches to complete one epoch. Batch training requires less memory and allows the model to update its weights more frequently, making training faster and more efficient. Overfitting happens when a neural network memorizes the training data instead of learning general patterns. Imagine a student who memorizes every answer from previous exams but cannot solve new questions. The same thing happens with AI. The model performs extremely well on training data but struggles with new, unseen data. To prevent overfitting, techniques such as dropout, regularization, early stopping, and using more diverse training data are commonly applied. Underfitting is the opposite of overfitting. In this case, the neural network fails to learn important patterns from the training data. As a result, it performs poorly on both the training dataset and new data. Underfitting can occur if the model is too simple, if it has not been trained for enough epochs, or if the selected features are insufficient. The solution is often to use a more powerful model, improve the input data, or allow the network to train longer. So far, we've learned about a basic neural network. But many real-world problems are too complex for a simple network. This is where deep neural networks come in. A deep neural network has many hidden layers instead of just one. Each layer learns different features from the data. For example, in image recognition, the first layer may detect edges, the next layer detects shapes, another layer identifies eyes or ears, and the final layer recognizes the complete object. Because of these multiple layers, deep neural networks can solve highly complex tasks with remarkable accuracy. Convolutional neural networks, or CNNs, are specially designed to process images. Instead of looking at the whole image at once, a CNN examines small regions and gradually learns important visual features. It first detects edges, then shapes, then textures, and finally recognizes complete objects. This step-by-step approach makes CNNs extremely powerful for image-related tasks. Today, CNNs are used in facial recognition, medical image analysis, autonomous vehicles, and many other computer vision applications. Unlike CNNs, which work with images, recurrent neural networks are designed for sequential data such as text, speech, and time series. An RNN remembers previous information while processing the next piece of data. For example, when reading a sentence, each word depends on the words before it. This memory allows RNNs to understand context. Although newer models like transformers are now more popular, RNNs played a major role in the development of modern natural language processing systems. Transformers are the most advanced neural network architecture used in modern artificial intelligence. Unlike RNNs, transformers can process an entire sentence at once instead of one word at a time. They use a technique called the attention mechanism, which allows the model to focus on the most important parts of the input. This makes transformers faster, more accurate, and better at understanding long conversations and documents. Technologies like ChatGPT, modern translation systems, and AI coding assistants are all built on transformer models. Neural networks have become a part of our everyday lives. They help unlock our smartphones using facial recognition, recommend movies on Netflix, suggest products while shopping online, detect fraud in banking, assist doctors in diagnosing diseases, translate languages instantly, and power intelligent chatbots like ChatGPT. In self-driving cars, they recognize roads, traffic signs, and pedestrians in real time. As computing power and data continue to grow, neural networks are expected to transform almost every industry in the coming years. Neural networks offer many advantages over traditional computer programs. They can learn directly from data without requiring programmers to write thousands of rules. They are highly accurate when trained with quality data and can solve complex problems involving images, speech, text, and video. Neural networks also improve as they are exposed to more examples. Because of these strengths, they are widely used in healthcare, finance, robotics, education, transportation, and many other industries. Despite their impressive capabilities, neural networks also have limitations. They often require massive amounts of training data and powerful hardware such as GPUs. Training large models can take hours, days, or even weeks. Another challenge is the black box problem, where it becomes difficult to explain why the model made a particular decision. In addition, if the training data contains bias, the model may also produce biased results. These challenges are active areas of research in modern AI. The future of neural networks is incredibly exciting. AI systems are becoming smarter, faster, and more efficient every year. In healthcare, they may help doctors detect diseases even earlier. In education, AI tutors could provide personalized learning for every student. Robots powered by neural networks may assist in dangerous environments, while AI could accelerate scientific discoveries in medicine, engineering, and climate research. Rather than replacing humans, the future will likely involve humans and AI working together to solve complex global challenges. Let's quickly review what we learned today. We began by understanding what neural networks are and how they are inspired by the human brain. We explored artificial neurons, weights, bias, and activation functions. Then we learned how information moves through the network using forward propagation, how errors are measured with loss functions, and how the model learns through backpropagation and gradient descent. Finally, we looked at advanced architectures such as CNNs, RNNs, and transformers, along with their real-world applications. These concepts form the foundation of modern artificial intelligence. Thank you for your attention and participation throughout this presentation. I hope you now have a clear understanding of how neural networks learn from data and why they are one of the most important technologies in artificial intelligence. From recognizing images to powering intelligent systems like ChatGPT, neural networks are transforming the world around us. If you have any questions, I would be happy to answer them. Thank you once again.